No. It's now recording. So I believe right now you guys are rounding on field extension stuff. At the end of last class, I think Jim gave you a parameterization of Pythagorean triples using Hilbert's theorem, and then you sort of talked about primitive roots of unity. Okay, so I'm gonna jump off from there, and then I'm gonna deviate a little bit from your PDF here, because Jim said I can't. But I'm really gonna do some really fun problems with using field extensions, applying them to number theory a little bit, and introduce number fields and rings of integers kind of indirectly, as you're gonna be talking about them extensively, and what I'm guessing is gonna be your last chapter, chapter 9. So let's go over it. I'm gonna try to keep it through number system for a second here. And let's go. So definition 8.7. Did he define primitive roots of unity last time, or?
That's the lesson.
Well, we'll do that again anyway. You say that tornado is a primitive and root of unity. Yeah. That is root of unity. And e to the m is not equal to 1. Or any less than that. Right? Kind of makes sense. Maybe you've done a little number theory and you've heard primitive mod p. It's a very analogous idea to what's going on here, right? So, right, for example, probably familiar with a lot of examples at this point, but this is always going to be a primitive nth root of unity for obvious reasons, right? And if we multiply this element, so if we raise this element to a power relatively prime to n, we're going to find the other primitive roots of unity, nth roots of unity over the rationals, right? Primitive roots of 1. -1 is not a primitive fourth root. Oops. Plus minus I. It takes 4 powers to raise I or negative I to get back to 1, right? Pretty straightforward stuff. So, yeah, I'm gonna skip ahead a little bit to definitions 8.7.1. Then I'm gonna deviate a little bit. Well, to give some very similar theorems to the ones that I've skipped, but for a specific setting. All right, so right. Say you get field. We define a cyclotomic extension. But that's what we're going to be interested in primarily today, cyclotomic extensions of order n to be splitting field of the polynomial x to the n minus 1. So you guys are good with all these definitions, right? The splitting field. So it's the smallest field of K, contains all the roots of this polynomial. Now, I'm going to now move away from the general field case and specialize to the case where the subfield is the rational numbers. And that's what we're going to be, that's the setting that we're going to be in for the rest of our time. Right, so. But maybe first I'll give a couple examples of cyclotomic extensions. And for simplicity, I'm just going to give some ones over that. You've probably seen this one. This is a cyclotomic field extension. What is the n in this case? Now, no, n, this might be confusing. N is not the dimension of the extension. Okay. It's bounds above the dimension of the extension, but this won't be irreducible most of the time. So normally the dimension of the extension will actually be strictly less, will almost always be strictly less than n. So what is the dimension of this extension over Q? 2, right. Right. And that's easy to see when we notice that Q join alpha is because Q is joining square root of -3, right? Because it's just you multiply by a rational, so add a rational, you get Q, you get square root of -3, right? And it's over the field of the rational, right? So this is a cyclotomic extension of Q, but it's also a quadratic extension of Q. And these are kind of the two nicest examples for what we're going to be looking at going forward. If we're looking at this polynomial over Q, how does it factor? Sorry, I don't think I heard x minus 1, and then what was the rest?
X squared plus x.
Yeah, right. X squared plus x plus 1. So this is why it's easy to see over the rationals, and while the other times the extension is not going to be of degree n, it's going to be strictly less, because we can always do this factorization over Q. And sometimes this is going to be irreducible, but very rarely. Only when n is prime. So in this case, obviously. Any questions so far? I think you've probably seen a lot of these objects already before. Right, more generally, right, you get this nice factorization. Which I always think is fun, because it's telescopic. Just cancel everything out, you're left with the smallest negative and the largest positive. Okay, so why am I talking about this? How do I stand right? Yes, it's the remote. Not this remote, but surely. There it is. Here it is. Thank you. So now I'm going to define something called a number field and talk about it a little bit. Have you guys talked at all about number fields? Okay, well, it's going to be a very easy definition considering how much time you just spent with field extensions. So definition. Let K be a field extension of Q. We say K is an algebraic, but often we drop the algebraic number field. If the dimension of K over Q is finite. These are all the finite dimensional extensions of the rationals. We call them algebraic number fields because they're kind of like our favorite number field, the rationals, right? The field we get from taking our usual numbers. But these field extensions and some of the subgroups can actually tell us a lot about the rationals and the integers themselves, and is what I'm going to get into today. So examples, our favorites, we got the Gaussian integers, right? We've got the example that we just looked at. We've got Q itself, right? Quadratic, dimension one, right? Straightforward. And I'll make the following note. I'm going to be using this term a lot going forward. We call a cyclotomic extension of the rationals a cyclotomic number field. And these fields play a very, very important role in the history of algebra and number theory, which we're going to brush on a little bit today. Any questions so far? So first, let me just talk about some of the nice properties that these cyclotomic number fields have. Remember, this is just going to be the splitting field of x to the n minus 1 over the rationals. So K is an cyclotomic number field. Then it has the following properties. One, is usual controlling tornado, where this is a primitive temperature unit. So what is it called? You guys know? Talk about when the field extension K is generated, by one element like this. Yeah, simple. It turns out any number field is simple over the rationals. All number fields are simple extensions, which is a very, very nice theorem. Big theorem, but we're not going to talk about it too much today. But in particular, just take a primitive nth root and adjoin it to K, any of them, that will get you the splitting field. And what's especially nice about this is its basis is what we call a normal basis, meaning it's just the powers of this, which are also its conjugates, right? Those are also the conjugates of the minimal polynomial, which is a very, very nice property to have. So 2F is an abelian extension of dimension Euler phi. So this, right, is just the row elements relatively cranked in it. Right. So this is nice. It's an abelian extension. Something else that we would like And then 3. Dialog of that over Q is isomorphic to the multiplicative. Multiplicative group of the cosets relatively prime. So first and foremost, it's Galois. We can see that in a couple ways, but first and foremost, its Galois group has the order of the extension, right? The order of this abelian group is precisely the order of the extension, which is sufficient to determine that it's Galois. But there's a lot of nice things here. We got simple, we got a normal basis, we got an abelian extension, everything that we could ever really dream of. Now, can somebody tell me how this group isomorphism might work? I've got a map that they can think of to go from the Galois group to this group.
They can bring it to and send it to any file.
Yes, essentially, exactly, right? I mean, I'm going to take some element of G in my Galois group, and I'm going to fix a primitive grid of unity. So I'll fix primitive. Then, of course, this sends it to one of its conjugates, but its conjugates are just other powers, right? And in order for them to stay primitive, and if they're not primitive, they won't be conjugates, they won't have the same minimal polynomial. I need to send it to a power that's relatively prime to n. Otherwise, if they have a common factor, it won't be primitive anymore. So sigma equals tornado to the R, where they're real prime. And so we can map this element to this coset. And it's not too hard to show that that's actually a homomorphism, that it's one-to-one and onto. So this is really, really nice. It's very easy to characterize all of the intermediate extensions. Right there, of course, going to correspond to subgroups of this group. Right, so in particular, what's going to happen if P is prime? Well, if P is prime, this is going to be cyclic of order P minus 1, right? So we're not going to have any intermediate field extension, right? Because there's going to be no subgroups except for the whole group and the trivial subgroup. So that's already very, very nice. So a lot of properties here, but the object that I really am going to be looking at is going to be a certain subring of these number fields. Any questions before I go on? And we start to get into kind of the fun part of the lecture.
Right?
Yeah.
So you said that if it's P, right, then why is P minus 1 will be with no subgroups?
Oh, I'm sorry. I didn't mean to say no subgroups. That's not what I was thinking about. You're right. Of course, P minus 1, it's going to have a lot of subgroups. They're all going to be, there's going to be a unique, is what I meant to say was, I was thinking about extensions of prime degree. When you have a cyclic extension, then there's going to be a linear ordering on all of the intermediate fields because there's going to be a unique subgroup of each order. Now, right, so let me not talk past myself here a little bit. This is isomorphic to the additive group, the additive cyclic group. This Right, so in my brain, I was thinking. Dimension P, right, but. This is cyclic, it's gonna be, have a lot of really nice properties. In particular, the intermediate fields won't necessarily be linearly ordered, but you're going to have a unique subfield for each, divisor of, this right here. So this is P minus one, the dimension of the extension. In abelian and cyclic groups, there's a unique subgroup for every, number that divides the order of the group. So we're gonna have a unique extension for every intermediate extension for everything that divides this. That's, thank you, I said something that was completely wrong. Getting ahead of myself. Right. So we are gonna be focused on a subring of the cyclotomic number field, in particular. Not Q if you're in the primitive group unit, but Z to join that primitive community, which is contained in that number field. So we get this little diagram. And the basic idea is that this, which later you'll come to refer to as a ring of integers, is like a surrogate for the integers in this number field. And what's going to happen is properties of this ring are going to help us determine properties of the integers in a lot of ways. And this was like a big breakthrough that happened in the 19th century. But from this point forward, I'm not going to worry about the cyclotomic number field so much as these specific subrings of the cyclotomic number. In particular, this is the integral closure of C here, but we're going to probably talk about that in particular more next time. Right. So the first question that I want to try to tackle is going to seem like it has absolutely nothing to do with these field extensions. And that's kind of the beauty of it. Maybe you saw this before in a undergraduate number theory class. So an odd prime P is the sum of two squares. If and only if P, does anybody know the rest? It's the condition on the odd primes such that they're the sum of two squares.
Is it like we're to one mod 4?
That's it. See, the key is it's always shoot. It's like congruence mod 4, which is it? Well, then you just remember 1 is the sum of two squares, or 5 is the sum of two squares, but 3 isn't. Well, this is almost all the primes, right? 2 is also the sum of two squares, 1 plus 1 squared, but right. So this is a completely number theoretic problem, but we're going to use number fields to prove it. In which direction do you think is easier? Forward or backwards? Forward is going to be easier. So let's say that b is equal to a squared plus b squared for some in. And right, when I say prime here, I mean rational prime. So I just mean integer like our normal primes. Well, let's look at a table mod 4 of all our elements. Module 4. When I square any of these elements, what do I get mod 4? If I square 0, obviously I get 0. If I square 1, I get 1. What is 2 squared mod 4? 0, and then 3 squared mod 4. So the only options modulo 4 are 0 and 1. Now, without loss of generality, I'm gonna say A is even and B is odd. Why can I do that? Well, P is odd, right? And when I square, if they were both odd, I would square them, they'd still be odd, and then I'd add them, they'd become even. If they were both even, I would square them, they'd still be even, and then I'd add them, they'd be even. So one has to be odd, one has to be even. Thus, P is A squared, plus B squared is congruent to, well, I said A was even. Either the even squared is 0, any even number squared is 0, mod 4, and any odd squared is 1 mod 4. So this gives me what I was saying. Simple modular arithmetic, nothing tricky here. The other direction is where things get a bit more interesting. We're going to let P be congruent to 1. Where do we go here? Well, the significance of this is, for us, that 4 divides. That's exactly what it means by definition for P to be congruent to 1 mod 4. Now I'm going to let alpha be primitive mod P. Do you guys know what I mean when I say primitive mod P in this setting for an integer? What I simply mean is that alpha bar generates this. So very similar to what we've been talking about. So we said this is a cyclic group. Yeah, this is a cyclic group of order P minus 1. I want this alpha, this integer I picked, its class to generate that. Meaning, if I take powers of alpha, I won't get a multiple of P until I hit the P minus 1 power, essentially. It's similar to the idea of primitive groups of unity, but just for now, we're going to allow beta to equal alpha to the P minus 1 over 4, which is shown must be an integer, right? So now what I'm going to do is square this. Can somebody tell me what this has to be congruent to, mod P, alpha to the P minus 1 over 2? It can't be congruent to 1, right? Because its order is P minus 1 in the group. What is it going to be congruent to? Well, it's going to be congruent to minus 1 mod P, because it squares, it's not 1, and then it squares to 1, because I get alpha to the P minus 1, which is the order of the multiplicative of the identity of 1. And minus 1 is the unique element of order 2. Right? It's the only class that squares to 1. So beta squared is congruent to minus 1 mod P, i.e. beta divides P squared. Sorry, not beta divides. P divides beta squared plus 1. With me so far? Okay. So what in the world does this have to do with number fields? Seems like we're just doing modular arithmetic. Well, this is where it's going to come in. In particular, I want to look at the number field Q join I and the Gaussian integers inside that number field. And what I'm going to do is factor this element. Gaussian integer. So remember, beta is an integer. How does this factor over the Gaussian integers? Non-trivial.
Beta plus I, beta minus I.
Yeah. So P divides beta minus I, beta plus I. P is an element of the Gaussian integers too. Fancy integers. So in the Gaussian integers, it divides this product, but clearly P doesn't divide beta minus I or beta plus I. Why? Well, simply it would have to divide both coefficients, and P doesn't divide in one. So what does this mean about P in the Gaussian integers? Not prime. Yeah, exactly. I did something here. Something bad in general, but it's fine. P is not prime, I said, therefore it's reducible. In other words, not irreducible. But prime's stronger than irreducible, right? So why can I say that because it's not prime, I know it's reducible? Why couldn't it just be irreducible and not prime?
Yes, that is not.
Yes. Z join I has unique prime factorization. In other words, it's a unique factorization when it's a UFD, right? So primes are irreducibles and irreducibles are prime. Okay. You're atomic and you have that condition that's actually equivalent to UFD. So if it's not prime, well, it factors into primes. So if it wasn't irreducible, it would factor as P times some unit, it would be prime, right? So it has to be reducible. So I'm gonna claim P factors only into two elements. I'm gonna let X be A plus BI, Y equals C plus CI, but I'm gonna write them as X and Y but remember they're elements of the Gaussian integers, not just integers. Why is it that they can only factor into two elements in here and not more? Well, refresh ourselves. What's the norm of P in here? Field norm. Q join I. P is rational, right? So what are its conjugates? Just itself. So we have a dimension 2 extension. So the norm of P, it's just P squared, right? But the norm is multiplicative. So this is the norm of xy. This is the norm of x times the norm of y. And these are both non-units. I should say non-units, right? Because it's a non-trivial factorization. So if x and y aren't units, then their norms can't be units, right? But p squared equals this product, right? So clearly I can only have two, both of which have norm one. Both x and y have to have norm p. P is equal to the norm of x. Is the norm of some a plus bi. in the Gaussian integers. What is the norm of A plus BI? Right. Multiply it by its complex conjugate, which is just what? That's it. So what happened? We turned a purely kind of number theoretic question into a question about factorization in the Gaussian integers. So we could rewrite this as instead of which primes are the sum of squares, it's which primes are reducible in the Gaussian integers. Those are actually precisely equivalent to actually ramifies up to a unit multiple. It's a square, so it reduces as well. But for the primes, the L primes, this question about being written as a sum of squares is equivalent to which one's the state prime in the Gaussian integers and which ones fail to be prime and thus split into two elements. So it's precisely a factorization question. And I really was hoping to do another one of these fun examples, but I think I'll just kind of talk about it a little bit instead. So last time, any questions about this? Oh, I forgot to move the thing. No, it's good. Yeah. We could consider y, but y is just going to end up being this by unique factorization. Y, I could have picked either one without loss. I could have said norm of y also equals p, and then it would have been so we get the same result, but what we also notice is p factored into these two elements, and by unique factorization, these are x. If x was a plus bi, y actually had to be a minus bi in the first place, right? So it's symmetric. But I could have picked either one. It didn't matter. So what I wanted to do, but I'll just kind of talk about it a little bit, is give you another way to parameterize the primitive Pythagorean triangles. Meaning the ones where there's no common factor between x, y, and z, which is trivial. Right? Primitive, right? Meaning b, c, d, and x, y, z. They have a common factor. Just factor out, we get a primitive one. So if we parameterize the primitive ones, we get them all, just take all the multiples. Right. So we have 5 minutes. So I'll just kind of talk about an approach you can take to this problem. You do something very similar. I'm gonna not think about these as elements of integers, but I'm rather going to think about them as elements of the Gaussian integers. So how does the left-hand side x squared plus y squared factor in the Gaussian integers non-trivially?
X plus I, Y.
like that. Right? We have x squared, the middle's canceled because the plus and minus, then we get y squared. Like minus y squared times I squared. It's a lot, right? So. So what we would have liked to show, and maybe Gene will do this next time. Our goal is to show that this element in the Gaussian integers is a square, right? It's some element squared times a unit of the Gaussian integer. And if we can do that, we write that element alpha squared as n plus ni, it's an element of the Gaussian integer, and then that allows us to immediately parameterize our the primitive Pythagorean triple. It's about maybe like 3/4 of a page. But I'm going to kind of talk about it a little bit more generally right now. And we use the fact that over here we have a perfect square and the unique factorization of the Gaussian integers again to say that, well, essentially any prime that divides this can't divide this. That's how the argument goes. And thus, because that prime divides this an even number of times by unique factorization, it divides this an even number of times. And then we get that this is a square, and we get a parameterization of that. It's really nice. So once again, we've transformed this question, this like purely number theoretic question, this kind of Diophantine equation, into a question about factorization in this ring of integers. And we're using extensively the fact that the Gaussian integers is a unique factorization domain. That's really, really important to this attempt. So I said that we were talking about cyclotomic number field in general, but I've only talked about the Gaussian integer, which is question which cyclotomic number field? First, second, third, fourth, fifth, sixth, fourth, right? Third and fourth also both degree 2, right? That's fine. Phi of 3 and phi of 4 both 2. This approach is really nice. And in 1844, Gabriel Lemay, a French mathematician, thought, I'm going to do the same thing for n instead of for 2. Instead of factoring it over the Gaussian integers, actually we're going to restrict ourselves to the prime case, right? I'm going to factor it over the z adjoin some primitive p3 instead. And you can do that quite nicely. And then he said, all right, I'm going to use the fact that this ring, this p cyclotomic ring of integers is a unique factorization domain to show that for any odd prime, there are no such solutions. I'm going to do the same kind of argument we did here, but using the oddness, he was able to derive a contradiction, thus showing that no equation of this form exists in the first place. And it's not hard to show that you can't have this for 4 either. And thus, because any number greater than 2 is divisible by 4 or an odd prime, that would be equivalent to proving Fermat's last theorem. So in 1844, he does this approach, right? He factors not over z adjoin I, but for every p, he factors over z adjoin this ring. And he uses unique factorization to derive a contradiction, and he gets a proof of Fermat's last theorem. But the problem was, these aren't unique factorization domains in general. Ernst Kummer had actually showed that the first one that's not, the first prime where it's not a unique factorization domain, is 23, 3 years earlier. So he gives a relevant extension. He says, instead of looking at things element-wise, these rings, they don't have unique factorization for elements, but their ideals still factor uniquely. And this is where ideals come from. he transforms a question about elements into a question about ideals, which are later defined more rigorously by Dedekind. We get something called Dedekind domains, which all of these rings widgets are, which is what you're going to talk about next time. But he was able to really beautifully transform this question, strictly element-wise question, into a question about how ideals factor, which we're going to get into the next time. And I wish I had more time to talk about it, but I don't. So, any questions? Well, thanks for your attention, and have a good weekend. I think I'll just take one of them.